Okay, so let's look at some more examples of Cayley tables in Z star n. So start with our mod 5 table. That's the Z star 5 Cayley table. We're dealing, of course, with multiplication, and this guy is going to turn out to be a group, which is kind of the whole point of this particular endeavor. So there are 4 elements here, 1, 2, 3, and 4. 1, 2, 3, and 4. We're going to be fortunate enough not to find any of the weird behavior we just experienced in mod 4. 1 times 1, 1, 2, 3, 4. 1 times 2, 3, 4. 2 times 2, 4. Right? 2 times 3, 6. Mod 5 is 6. Mod 5 is 1. 3, 2, and 1. 4, 2. 2 times 3 is, of course, 1 again. Last but not least, 2 times 4, 8. Mod 5 is 3. So this completes our mod 5 Cayley table nicely. Our mod 5 Cayley table worked out really well. Let's see. And keep in mind that basically how mod 4 functions, how mod 5 functions, is in mod 5 we can subtract as many 5s as we want from a number, as long as the result is not negative. This means that one of the most efficient ways to do mod quickly is just to look at multiples of the mod. So 5 is nice because we can take away any number that's close to 10. So yeah, mod 103, 100 is close to 10, it's 10 times 10 in terms of linear multiples. And so 103 minus 100 is equal to 3 mod 5. Let's look at the mod 6 Cayley table under multiplication. This guy, it's just these two numbers, 1 and 5. In fact, we've already seen a variation on this Cayley table several times before. And this is interesting. This starts to give hints as to what the actual nature of this set is and how we can construct it a little more easily. So let's go on the Cayley table for Z star 7, and you should think to yourself right now and wonder what it's going to be, what it's going to look like. That's right, it has all the numbers up to 7. Interesting, interesting what we got going on over here. That's up to and not including, of course. Pretty big table to fill out here. I'm going to start with my 1 columns, because that's nice and easy. Alright, move over onto my next column, see if I can get all the numbers in there sorted out. This is my 2's column, so I've got 2 times 2 is 4, 6, 2 times 8, mod 7, it's 1, 3, 5. Alright, 3 times 2, 6, 2, 5, 1, and 4. All right, 4 times 4, 1, 5, 2, 6, and 3. 5, 3, 1, 6, 4, and 2. And all this is multiplication mod 7. Multiplication mod 7. But we'll see that this particularly nice pattern is emerging here. And that some Cayley tables have this kind of cool structure. Even better, some of these multiplicative Cayley tables just involve every element. So the set here is actually just the same as the set Z7, except for the removal of 0. Let's make our Cayley tables a little crazier. Here's our mod 15 Cayley table. One, two, three. Nah, no 3 in this one. Oh, that's a shame. Messed it up. 1, 2, 4. 7, 8, 11, 13, and 14. These are the members of our set. 1, 2, 4, 7, 8, 11, 13, and 14. Which opens up a question, which is how do we find these consistently? It might be rather nice, as opposed to using the previous technique where we had to find a particular 0 and cancel that entire row. Here we would have to do a big 14 by 14 table in order to actually pull that off, which seems pretty lame. This is a only 1, 2, 3, 4, 5, 6, 7, 8 by 8 table, which, you know, is still intensive enough in its own right. Yeah, close enough. All right. Let me fill in this table. Again, the 1's nice and simple. All right, just straight up multiplication by 1. 2's also nice. I'm just going to go. Whoa, did I try to. Silly me. 2, 4, 8, 14, 1, 7, 11, and 13. Multiplication by 4. 4, 8, 1, 13, 2, 14, 7, and 11. Multiplication by 7. 1 times 7, still 7. 2 times 14. 4 times 13, of course. 4, 11, 2, 1, and 8. 7 times 14, mod 15, 8. 8 times 1, 8, 1, 2, 11, 4, 13, 14, and 7. There is actually an internal pattern here, if you notice. It's a little more complicated than the previous ones we've been experiencing, but 11 times 1 is 11, 7, 14, 2, 13, 1, 8, and 4. 13 times 1 is still 13. 11, 7, 1, 14, 8, 4, and 2. And then we should notice an interesting pattern here with this last guy. We just have the top numbers reversed. 14, 13, 11, 8, 7, 4, 2, and 1. So that's kind of a nice relationship to be aware of. So here our Cayley table's gotten pretty funky, and it's become pretty necessary to figure out the answer to the following question, which is which elements are the members of Z star N. And the answer to this is actually relatively straightforward, and you can check these tables and make as many as you want to prove this to yourself, or you can go back and check the previous definition of Z star N, and that should do you most of the way here. But this is a relatively easy set to figure out. It is the set Zn, right, starts as Zn, minus, except for, take away, prime factors and their multiples. This explains why each time we ran into a prime, we had no issues, right? Our prime here, totally good. Prime factors of 6, 2 and 3, 2 and 3 are gone. For 15, 3 and 5 are gone, and so is all the multiples of 3 and all the multiples of 5, right? No 3, no 6, no 9, no 12. No 15 either, obviously. This is mod 15. No 5, and no 10 from the 5 factor. Prime factors and their multiples. Quick reminder, and 0. Because b, or any number, 0 times b, mod n equals 0 for all b in z star n. So for z star 15, this is equal to the set of all numbers from 1 to 14 except prime factors and their multiples under mod 15. Of course, we know from this, and we could break down the prime factors and figure out their multiples and do it directly, but we know from this that this is just the set 1, 2, 4, 7, 8, 11, 13, and 14.